How's everybody doing out there? Well, hopefully everybody did a great job on chapter 2, and we're moving out of our descriptive statistics into our probability section. So probability is something that we're going to use a lot when we get into inferential statistics. But fortunately for us, the calculator is going to help us calculate a lot of these probabilities. So here, what we're going to do is go through a variety of different types of probability techniques throughout the chapter. And so we're going to start off today with just some basic introductions, some definitions, and talking a little bit between the difference of empirical probability and theoretical probability. So for the most part, probability is just a way of describing how certain we are that a result of an experiment or activity is going to occur. And so obviously a higher number like 95, 98, something like that means that there's a good probability that that event is going to occur, like 20%, 30%, something like that would lead us to believe that it's probably very unlikely that that event would occur. So probabilities are, of course, percentages. So we're going to be using some percents and things like that. So between fractions and percents to talk about our different probabilities. Just to give us a little background, some of the vocabulary that we're going to be using for probabilities. So the outcome is just one possible result of an experiment. So if we were flipping a coin, we've got two choices, heads or tails. So flipping tails, for example, would be the outcome. If we were rolling a six-sided die and rolling a 3, that would be the outcome of that event. So the sample space gives us a list of all the possible outcomes that could actually occur for whatever event that we're interested in. And so I've got some examples here. So if we had we're rolling a six-sided die, then the sample space would just be all the possible numbers 1, 2, 3, 4, 5, and 6, like we have here. And so notice the way we list these, we just kind of list them out in this kind of brace notation, and the S just labels what that set is called. So another way that we can figure out a sample space is by drawing like a tree diagram, for example. So that's what we've got here, a little tree diagram. Could help us to figure out what the sample space may look like if we need it. And then finally, we can also draw a Venn diagram. So for those folks that have taken Math 110, so this is another way that we could actually kind of represent what our sample space would look like, or a way to like figure out how many elements there are in our sample space. All right. So our events are the outcomes from actually doing our experiments. So for example, I've listed 3 different events that could occur. So we could roll a 4 on a six-sided die, we could roll an odd number on a six-sided die, or we could roll a number greater than 2. So there's a variety of different events that we could actually have occur for these guys. And so a lot of times the way we'll write out these events are, we might write it kind of in like a function notation, so P parentheses A, or if it's obvious like what we're talking about, we could actually just write it out in words. So for example, P of rolling a 4 is the same thing as saying what's the probability of rolling a 4. Or if we know we're talking about six-sided dies, we can just simply say just the probability of a 4. So if we know the context of the problem we're working on, we can make it even simpler than that. But all right, so those are all the definitions that we're going to need in order to go over this section. So first thing we want to do is we want to do a little practice trying to figure out what some different sample spaces would look like, and that's going to help us later on when we're going to calculate our probabilities of these guys. So we know if we were just flipping one coin, so if we were flipping one coin, our sample space is just going to be either heads or tails. We only have 2 possibilities in that case. Now, if it goes up to where we're flipping 2 quarters at the same time, then what could happen is we could have like a heads and then another heads and tails. So we have to like kind of think about each coin as its own location. So the way I'm going to think about this is going to be like the first quarter. and then the second quarter. So since these are two different quarters being flipped at the exact same time, so we can have, like, for example, two tails occurring or something like that. And so I'm going to write these out in terms of ordered pairs when I set up my sample space. So if I'm going through, my possible flips for my sample space could be, I could get heads with the first quarter, and then heads with the second, or I could get heads with the first quarter, tails with the second. I could get tails with the first, heads with the second, and then finally tails and tails for the third. So notice when we had one coin, our sample size was 2. When we've got 2 quarters, our sample size became 4 in that case. So now let's go up again. Let's add a third quarter into the mix. So now, instead of having an ordered pair, we're going to have an ordered triple. So we're going to have our first quarter, second quarter, and third quarter in this case. And so again, we want to think about what the sample space would look like for this situation. So with this one, I'm going to try to make sure I organize it in a nice way. And so I'll talk about it as I'm going along, so that way you can see how I did it. So what I'm going to do is kind of start off like we did last time and have all 3 coins be heads to start off with. And then what I'm going to do is I'm going to leave the first heads fixed and kind of vary through the different possible tails that we can have for the other choices. So in this case, we could have heads, heads, tails, or we could have heads, tails, heads. And so now I'm going to go and allow that first coin to be changed from a heads in this case. So we've got, so this could be tail, heads, heads. And so with this one, what we've got is we've got every possible way of having 2 heads and 1 tail now. So now we want to kind of change it around and think about how many possible ways are there to have 2 tails and 1 head. So I'm going to go through and kind of change up the different tails. So with this one, I could have tails, head, tails. I could have tails, tails, head. Or I could have heads, tails, tails. So those are the only possible ways of having 2 tails and 1 head. And then finally, the only other possibility left are 3 tails. So in this case, we have tails, tails, tails. And if I've done this correctly, there should be 8 total in our sample size. So 1, 2, 3, 4, 5, 6, 7, 8. So perfect. So our sample size is 8. And so you may recognize a pattern of where these numbers are actually coming from. But so what we've got is we've got 2 possible choices for our outcomes. So we've got either heads or tails. And then the number of coins that we're flipping is actually going to be kind of the exponent for each of these answers. So in the flipping of 1 coin, for example, our 2 possible outcomes were heads or tails, but we only flipped 1 coin, so 2 to the first gave us our number 2. For our second one, we had 2 possible outcomes, heads or tails, but we flipped 2 coins. So if I raise that to the second power, that gives me 4. And for the last one, again, we still had 2 possible outcomes, but we had 3 coins. So 2 raised to the third is where my 8 comes from. So you can use that little shortcut sometimes if you're trying to figure out, did I actually get the right number and things like that. So because it can be tricky to make sure you didn't miss any when you're writing out your sample space. But all right, so let's look at the last one here. And so this one's kind of a nice one. This one's going to get used a lot. So make sure you kind of keep track of this one because this is a nice example. It has a lot of pretty big size sample space. So let's suppose we're rolling a black six-sided die and a white six-sided die, where the black die is going to be the first, the white die will be the second. So we've got our two dies. And so again, we're going to write these in ordered pair form. And so what would our sample space look like? So this one's going to be pretty big, so I'm not going to use the set notation, but I do want to show you how I set this up to make sure we don't forget any as we're writing them down. So what I'm going to do is I'm going to assume that the black die rolls a 1 and stays a 1 throughout the whole entire first column, and I'm just going to vary all the different possible white die numbers that we can get. So in this case, we could have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And so now I'll just do the same thing over and over and over again, fixing the first die and then cycling through all the different possibilities. So now we could have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, and then 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and then finally 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, oops, and 6, 6. So finally, after all this writing, we see that we've got 36 possible outcomes that can occur when we're rolling two pairs of dice. And so again, if we think about our rule above, for each outcome, we had 6 possible outcomes. So 1, 2, 3, 4, 5, 6. So in that case, our base would be 6. And we had 2 die. So if we raise 6 to the second power, that's where our 36 is coming from. So again, this gives us a nice way to check our answers and make sure that we've actually written down all the possible outcomes that can occur. All right, so hang on to these. We're going to use these a little bit later in some actual probability problems. So for now, what I want to do is talk about some rules of probability and make sure we understand what these are. So again, since a probability is a percentage, then it's going to always live between 0 and 1, where 0 would be, for example, 0%, 1 as a percentage would represent 100%. So there's no negative numbers, there's no numbers bigger than 100%, so it always has to live between 0 and 1. The probability of A equaling 0 means that this event can never occur. It's impossible to happen, and so there's a 0% chance that that's going to occur. Probability of A equaling 1 means that the event's always going to occur. So again, this means it's 100% probability, so no matter what happens, that event is always going to occur. It's always going to happen. All right, so the other nice thing is if you take the probabilities of each individual event, and if you add them all up, then the sum of those probabilities are always going to be equal to 1. So for example, if we look at like the probability of flipping a coin, like we've got the probability of heads would be 50%, the probability of tails would be 50%. If we add those two together, that's going to give us the 100%. So again, this trick is going to be useful later when we do some other stuff related to probabilities. But all right, so now what we want to talk about are our two different types of probability. So we've got our empirical probability and our theoretical probability. So empirical probability is where we actually observe what's going on and base our probability off of those observations. So for example, if we wanted to find the probability of rolling a 1 on a 6-sided die, well, what we would do is roll the die a bunch of times, count up how many ones we got, divided by the total number of die rolls, and see what kind of answer we got. So we're actually doing something with an empirical probability. Or a theoretical probability, we're using what we assume should be true about a die. So for example, a die has 6 sides. So in reality, the probability of rolling a 1 should be 1 divided by 6, because there's only one way to roll a 1. So that would be theoretical probability, where you're using what you think should be true about the object to go from there. So to calculate our empirical probability, what we're going to do is take our observed, so the number of things that how many things total that we had in favor of what we were looking for, divided by the total number of all things that we did. So whether it's die rolls, flipping coins, whatever they happen to be. All right, so for the next example, so normally I would have you guys do this in class together. Everybody be flipping coins all over the place and be making a big old mess. But for now, I'm just going to show you a little app that I found that's going to simulate the same thing, and I'll kind of fill out the table. And again, we probably know what this probability of flipping heads would be from a theoretical perspective, but what we want to do is see if our empirical matches our theoretical. And so we're going to go through and do 1 toss, then 5, then 10, then 20, and then 50, and I'll kind of jot these down as we go along. Now in the first case, number of tosses 1, well if we only flip the coin once, we're only going to have a choice of either heads or tails. So we're either going to get 0 in the heads column or 1. And since our total number of rolls is 1, we're either going to get 0 over 1, which is 0, or 1 over 1, which is 100. So again, this won't, doesn't obviously give us the 50% we're probably thinking about, but it'll build us to where we want to go. All right, so we flip over to our little app I found here. So in this case, I want to flip just 1 coin, so I'm going to hit the flip coin button. So in this case, I got 0 heads, 1 tail, so my percentage of heads was 0. So if I go back here, I got 0 here. My probability would be 0 divided by 1, which of course is 0%. So now let's go back and do this 5 times and see what happens. So we're going to get 5 flips. So let me change the number of coins from 1 to 5. And so in this case, so that's kind of weird. I got 4 heads and 1 tail, which can happen. That's totally fine. So here I'm going to get 4 out of 5, which gave me my 80%. So again, a far cry from the 50 that we were hoping for. So let's jump up again. Let's try 10. So if I flip 10. Oh, now this one we got lucky. So notice we got 5 heads, 5 tails exactly. So this is exactly 50%. Oops, wrong thing. 5 over 10. So let's try 20 and see what happens. So notice in this case we've got 11 heads, 9 tails, so a little bit more heads than tails, but still not too far off. So 11 out of 20 is our 55%. And then let's do 50 here real quick. So this one's a little strange too. So we've got 22 heads, 28 tails. So again, not quite at the 50% that we were hoping for, but again, that happens when you're doing empirical probability. And so for the last one, I'm going to put, say, 1,000, just to be crazy here. So since we can do that. Hopefully this thing doesn't blow up on me. All right, so we got 498 and 502. Which gives us 49.8%. And so in that case, we can see it gets really, really close to 50%. And that's kind of the point with empirical probability. So we did get lucky at 10, that we saw that it was exactly 50%. But notice that, 1, of course, was not very good at all. 5 wasn't very good at all. We got lucky with 10. 20 wasn't too bad. 50 again was a little low, but not too bad. But if we were to keep doing this over and over and over and do a 10,000, 100,000, eventually what we would notice is that this empirical probability is going to kind of increase that theoretical probability, and it'll start to equal 50% all the time. All right, so in this case, let's have you guys work on practice 2. So the main thing you want to do with these guys is make sure you calculate the total. So we do want to go in and fill out the total for these, and then take our individual numbers for the top. Our bottom number is going to be the total. Calculate our probabilities. And I'll come back in the next video and we'll talk about our theoretical probability of after you finish these.